Thank you. Good evening, everyone. Today I will presentation but what we had our help from the Simpa School about coding theory. We met I'm with my partner Panji. I think he's not still here. He will come soon. Actually, today I will sharing about coding theory. This is only about the some introduction and the application in cryptography. Okay, the position is about the material. Is from introduction, like Solomon, secret code, and then coding theory in cryptography. Let's start with the introduction. Coding theory is about how to recover or receive message which transmitted in noisy channel. Example, movie A, we send with alpha, B we send with beta, and etc. Example, repetition code. Suppose you want to send a message HI exclamation mark with the repetition code. The message is sent as HII exclamation mark exclamation mark. If receive word is HII exclamation mark, HII question mark and exclamation mark, the error only detectable but cannot corrected. It means we know there's a error in the message, but we can correct the message. With the repetition code, the message can also be sent as H H I exclamation mark triple. If the received word is I exclamation mark question mark exclamation mark, the error is detectable and can be corrected. The question is, you can send line n times for each symbol. How many errors you can correct? So the answer is the floor of n minus 1 over 2. The information rate is 1 over n. How we have this? We will learn it next. Okay, the second example is about parity check. I want to send a vector in F2 to the 4, M1, M2, M3, and M4. But I add some redundant that definition by like this. R1 is M1 plus M2, R2 is M3 plus M4, R3 is M1 plus M3, and R4 is M2 plus M4. And alpha is the sum of the others entry. Then I send M1, M2, M3, M4, R1, R2, R3, R4, R5 in F2 to the 9. You can correct one error with this code. Then the information rate is 4 over 9. Yeah, we will know how we get that for the next. Next example is call is Hamming code. I want to send M1, M2, M3, M4. I add some redundant. That's the definition by this three condition R1, R2, and R3. Then I send M1, M2, M3, M4, R1, R2, R3 in F2 to the 7. So actually the coding theory is about to send a message this, but in the channel we change to this vector. So we try to avoid the some errors. So we define some redundant. With this redundant, we can detect or correct. Is there any trouble with our message? This our message. Okay, then this the some important term in coding theory. Let script A be a set of key symbols. We call it the alphabet. Let A power n script A power n be the set of n tuples, vector x, x1, x2 up to xn with entries in script A. A code C is a subset of script A power of n. The elements of C are called code words. If the numbers of C is m, we say that it has size m. If m is key power of k, then C call an nk code. The number n minus k is n minus logarithm key m is the redundancy. The information rate is R, which is log m over m. So we back to our example. Example 2, parity check. We know this set of alphabet is F2. The key is, because the key is the number of alphabet is 2. No is 0 and 1. Then we have the message, the coded, the code C is about, in a because this in F to the 4 is, it means that the C is to the power of 4. And then the length is n, because we see from this is the message. The length is m, and n is 9, k is 4, and then the redundancy n minus k, 9 minus 4 is 5, and the information rate 4 over 9. Okay. How with this hemming you can try it by yourself. Okay, next. So, okay, we back for the sample before. So it is called, because the length is 9, dimension is 4, and the distance is not yet it's only like this. Distance we will start in with this definition. For X and Y alphabet alphabet power n, the Hamming distance is defined as the xy. This is the number of set of I in the set of 1 up to n, with xi is not equal to yi. So example, we have, sorry, we have x is 1 0 0 1 1 0 1 1, and y is 0 0 1 1. So the distance x and y is, the difference is same, is different, is same. So the distance is 3. So the proposition 1 is about the property of the the distance, distance. So I mean, if we try to have this, you know, this that is a bit equal with metric measure, with the three axioma is which is the triangle inequality. Okay. Next, we will define a special code that have so many applications in coding theory. Its name is a linear code. So a linear code is a linear subspace of f key to the n. We say that it is a nk key code. Sample for the parity check and the Hamming code before is a linear code. The minimum distance of a code C, a subset of script A power n, is defined as the minimal of the distance of all code word in C. And then the linear code we call by parameter is nkd key. Key is as the alphabet F key. Next, let's see the NKD code and G1 up to GK is a basis of C. So this is a vector actually uh, in this element in this vector is in F key to the power of to the n a basis of C. So the matrix G matrix G is we say represented as the row vector G1, G2 up to GK is a generator matrix of C. So for U, vector U in F key to the K, UG is code word. So we call U is vector information vector. But UG is code word.
Bu Juli,
Yeah.
there is a question in the chat session, chat column.
Mhm.
Do you want to answer the question now or in the end of session?
Uh, I think is in the first session of this lecture. Okay.
Okay, so the questions session is in the end of the
Yeah.
session. Okay.
After the linear codes, after about linear codes, I will answer
Ah,
the. Okay.
okay, okay. Thank you.
Okay. Thank you. So next, how with the code before we have how we will determine the generator matrix. So we see from okay back for this. So because this 7 for linear codes over F2. So the generator matrix it will be 4 times 7. We say this orders 1, 2, 3, 4. Okay, we have this. Okay, because the entry M1 up to M4 is just independent. So we can write like this. But the redundant is we in fifth column up to the seventh column is R1 up to L3. We have M2. So we have the in this 0, 1, 1, 1, 0, 1, 1, 10 and 111. Okay, you can get. So this the generator matrix of Hamming code. How about the parity check before? You can check by yourself. Okay. Next up is given a word x in f key to the n. Its weight is with x, which is the number of support x, where support x is the set of I in the set of 1 up to n, where xi is not equal to 0. So example, we have x is 11010. So the support of x is, because this is not equal to 0, but the first entry is 1, 2, 0 is same, not, no, this is yes. So the support is 1 to 4. Remark, the weight of x is same with the distance of x with the 0 vector. The second proposition is for a linear codes, the distance of code is the minimum of width of x. It is for x in C actually. But minus 0. Okay. So how to prove that we know the xy is same with the x y minus x, because we can substitute both the code word with same. It will be not change the distance. So from this we get it mean that the distance of this is same with distance of 0 minus distance of 0 with y minus x, or is same with weight of y minus x. Okay, next, let's see the NKD code. It can correct up to floor of d minus 1 over 2 errors. So from the example before, parity check, as we know, this distance we not yet get. So if you check all of this code in this code parity check, we will have that the distance of this code is 3. So you can, because the correct is 3 minus 1, 2, 4, same with 1. Okay, next proposition is for all linear codes. First is called Chiltern bound, that the distance of code minus 1 is less than the redundancy. And the second, and because of this condition, there's a condition where is only for the equal, this so the code with the condition where the minus 1 is equal to n minus k is called maximum distance separable or MDS code. Okay, next, we already have talk about generator matrix. So then let's see the NKD key code. Operator check matrix is n minus k cross n matrix with entries is in F key such that C is kernel of H. The proposition from this definition we have property that H multiply with the G transpose is same with 0, 0 matrix, this matrix. Same with, it's the same with G multiple with H transpose. For the proof is only use the fact about this that C is in the kernel of H. As we know, all of G1 G1 up to GK is in, actually G1 and GK is in C. So because is kernel of H, so the multiplication of H with G1 up to GK is zero matrix is zero matrix. Okay. So example, given linear code C with the generator matrix G 1 0 1 2 0 1 2 1 over F3. It's a 4 2 3 code. Then the parity check is 0 0 1 1 and 1 2 2 0. So actually, linear code is not only have a unique generator matrix or parity code. So it will help the other form. Example for this we can have the others form of parity check is confirmed by this by this theorem. If G is the augmented matrix in IK with X is the standard form generator matrix of NK linear code, then the standard form of parity check matrix is the augmented matrix of X min X transpose with I minus K where I minus K IK is identity matrix with size K cross K. So from this example, because it standard form is I2 and the X is 1 2 to 1. So we have the minus X is 2 1 1 2 and we have this transpose. So we have the parity check is 1 and with 0 1 1 0. Okay. Next, the next property is about the relation of code distance with the column of parity check. D is smallest integer such that the columns of H are linearly dependent. Okay, of the proof. So sorry, there's a misreading about this. Actually, this is not both side proof. So first we have to prove that the column is linear dependent, and then we prove that D is the smallest integer. First, for the first, let C is in C, such that weight of C is D. Then we already have that because the some element of kernel, it's cause the C transpose is 0. The same with the sum of HI, rho dot CI is 0. Because we know that the 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 weight of C is D, so we have support of C. Actually, we can define as A1, A2 up to AD, ID. So we have that the sum of HIG dot ITIG is 0. Thus, the G column of K is linear dependent. So there's nothing wrong with this. Then we prove that D is the smallest integer. If there were the minus one column of K were linear dependent, that we will get a word C prime in FKN with its weight is D minus one, such that H dot H multiple with say prime transpose is 0. So we just mean that C, sorry, it means that C prime is in C. So that's contrary with the fact that D is the distance of the code, cause this is the minimum. So it means that D is the smallest integer. And next, the dual of linear code, let's see B and KD code. The dual code C orthogonal is defined as the set of X in F key to the N. For all C in code, the scalar product is 0, where scalar product is defined as usual in Euclid, or even though it's in infinite field F key, but is have same definition with Euclidean in Euclidean space. Okay, tadi dicek matrix for C is a generator matrix for C orthogonal or the dual of linear code. And then dimension of its dual is I minus k, and the dual is called n minus k key code. And the orthogonal of C orthogonal is the code itself. The next definition, C is self-dual if the code is same with its dual. Example, dual of Hamming code is generating by H is with this matrix. It's because the dimension the length is 7, the dimension is 3, and we can count that from the count that the by ourselves that the distance is 4. Okay, now let's see. Okay, next session is about actually when we send message, there's something noise or trouble in the channel. So this in this part we will try to understand how the method to correct or to correct the error we have is called with syndrome decoding. When we decoding, so decoding means we change the message. Actually we have the message we have is the code word in channel, something are error with this. So but there's something wrong with this, some error. We try to correct this. How we can correct this? We call the systematic to fix it is with syndrome decoding. Okay. Let C be a NKD code with control parity check matrix H. Let X be in FKN. Then we define that syndrome of X as the function of X. X is the multiplication of X with the H transpose. The proposition, or if X in the code, linear code, so the syndrome of X is 0. So for the proof, C, because C is the kernel of H, C uh, in linear code, it means it's C transpose is 0, and it means C multiple with H transpose is 0. If C is in C is sent through a nocicle, the word R is received. So we have C, we have, sorry, we have code word C, we send through channel, but as noise, noise channel, and we receive that the word is R. So with the syndrome decoding, we count the syndrome of the C, the R, the syndrome of R, we can get what actually what we send. So we can have from this SR is SC plus E is equal to CE H transpose, and then we have because C is in the linear code, we have it's equal to 0. Because the error must be not in the linear code, so the the apa the result is a H transpose is the syndrome of factor E. So for example, given a 532 over F2 code with generator matrix this and parity check this. Let R actually this code there different with scalar is a vector 101110100 is the receive word. Then the syndrome of R we count with we multiply with the H transpose. We have the syndrome is 010. That's not same with the zero vector. How to correct this wrong? How we correct this wrong? By searching through some word with minimum weight. So actually, we try to count one by one. You can have because the length of the code is 5. So you try to multiple the minimum weight from the minimum weight because mm, we already know that the error must be a, a factor with minimal weights. So we try to multiplication word with minimum weight with the H transpose. So example 1000 or 01000 and etc. Until we have the syndrome, we count the syndrome. If the syndrome is equal with 0, 1, 0, so the trouble is the error is the 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 factor. Okay. So after that we can have the error by, in this case we have the error is 0, 0, 1, 0, and then we determine that the send message actually r minus e, that is r, will know that r is 1, 0, 0, 1, 0, 1, 0, 0 minus this. So we have the message actually 1, 0, 1, 1, 0. Okay, that's for our first session for linear codes and introduction. Okay, I think we can try to see what the question.
Have you seen the question, Bu Juli?
Sorry, not yet.
The question is about in the column chat. There is question about information rate.
Information rate.
Yeah.
Okay. Oh, sorry. Okay.
So Mas Muhammad Siddiq asked about what can we interpret from computing information rate.
Okay, from the information rate, we can go. Sorry. Okay, because the information rate is, okay, the information rate that are the dimension of code over the length of code. Because we see that the example, this the code word we have with length n. So we already know that actually our method is interpret as fact and as our vector information is actually in alphabet AK. But because if we only send in AK, maybe there's something wrong in the channel. So maybe if example we send what in information rate is 1, 0, 0, 1. If something trouble with the channel, we have 1, 1, 0, 1. So actually we know actually in the set of AK. So we don't have something that we help us to know what is the trouble with this information or the message. But if we change with word with more length, have more length, so we can detect or correct is there something trouble with the code word we receive. I think is the I can answer for the question.
Uh,
Oh, Mr.
okay, Mr. Siddiq, Muhammad Siddiq.
Uh, I'm sorry, but I still don't understand what
Okay,
the explanation.
okay. Okay. Actually, we know this some channel, okay? Channel we send X this our message. We can send in the channel, but something in this channel maybe noisy. There's maybe some plus error. So if we send this X with this channel as X, so the one we that receive our message is maybe get this because uh, we know the set of our ini in the set of our sorry. Hmm, the set of our message is in the set of alphabet of power of k. So we can get we can detect or correct it any trouble with this because it's also in AK. But if we change this message to X with word word or code word C, that's actually in a K N, which is N is greater than K. So with the the define of the code we have, we can detect, we can try to detect or correct it, the wrong in the noisy channel. So that is the interpretation here. So we count that if 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 actually n same with n, if we get that the rate is 1, so we don't know actually what we'll do with the error message. Okay, so with the less ratio of k over n is maybe more useful for for decoding our message. I hope I can explain what your question.
Okay, thank you for the explanation.
Okay, thank you. Okay, we will have take a rest about 5 minutes before we start. About 3 minutes before we start the next session about the Salmon codes. Okay. Okay, we will start again with the next material about Reed Solomon codes. For example, QR code use Reed Solomon codes over 256 or the extension of binary code uh, f to the power of 8. Reed Solomon codes were developed by Irving Reed and Gustav Solomon in 1916 in their article titled Polynomial Code over Certain Finite Fields. Okay, we start with the theory. Let's see NKD linear code. We can see that NKD linear code as image of injective linear map P from FKK to the FKN, where N must be greater than K. Choose the code C is the image of P is a subspace of dimension K of FKN. To define the Solomon code, we will construct our injective linear map from FKK to FKN. Let a factor in FKK that is A0 up to AK minus 1. Then consider a polynomial of degree K minus 1 with the coefficient is this vector. Px is A0 plus A1x up to AK x power of K minus 1 in Fkx. Now we choose distant elements n within K and K, that is beta 1 up to beta n in Fk. Consider the map is the map P is from Fkk to Fkn. There is factor F0 up to AK to the double in Fkn by subtraction this distant elements. The first question is P is injective if P beta 1, P beta 2, P beta n is equal to K beta 1, K beta 2, and K beta n with Px and Kx is the polynomial in Fkx with degree is K minus 1. The polynomial P minus K has n distinct roots, which is n is greater than K. Hence, P minus K is 0, such that P is equal to K. Thus, the code C image of FKK is the set of P beta 1, P beta 2 up to P beta n, where P is in Fkx of degree K. Such that the size of C, sorry, same with this, is K power of K. Then the next question is C linear? C linear? This means that this trapezoid is linear transformation. But equivalently, we have that P A1 up, sorry, it's not A1 in A0. A0 up to AK minus 1, we map to the P beta 1, P beta 2 up to P beta n. We arrange that with this defined polynomial. Okay. Okay. By its row. Then we have that is equal with the multiplication of this matrix with the factors. So this matrix called Van der Moon matrix. Therefore, C is a linear code. Not the submatrix A. So if K, we already know that K is less than n. The submatrix, so in something in this part actually. Has determinant is not equal to 0 since the beta 1 and beta j are all distinct for ig is between, sorry, between 1 up to k. Hence the rank of A is k, so that rank of the image P is k. Thus C is image of P is a NK linear code over FK. Next, all with the distance. So let X is a code word in C for any X. We have to define that X is before P beta 1 up to P beta n. Then the weight of X is the number of I where P beta I is not equal to 0 because the length code is n is same with the n minus the set of the number of the set of I where P beta I is 0 because P has degree less than equal K minus 1 and this form has is less than equal K minus 1 so that the weight of X is greater than greater or equal than n minus K minus 1. So we already know that about singleton bound because we know that uh, C is linear code. C is linear code. So the singleton bound. So because is hot for uh, this and this. So we got the distance is n minus k plus 1. Equivalently, you could have so that is existence of code word of weight n minus k plus 1 by polynomial interpolation. Thus, C is nk n minus k plus 1 linear code over fk. Okay, this some little explanation about the Solomon code, but for you more know, you can learn by yourself. RS code are example of cyclic code where beta 1 up to beta n are distinct. So what is cyclic code? A linear C of length n is called cyclic if code word C0 up to Cn minus n in C implies that Cn minus 1, C0 up to Cn minus 2 in C. So there's a move forward from the last entry to be the first entry. Remark, cyclic code as invariant under or cyclic shift. So is there's a move from the left to the right. Example, C is the set of 0, 0, 1, 0, 0, 1, 1, and 1, 0, 1 is a cyclic code over F2. For example, this, if we change cyclic shift 0, 1, 1, is actually in C. So what is our goal? Given FKN, find of cyclic code of FKN. So we will try to have this solution with this explanation. We're going to interpret code word as polynomials. Let's see be a linear code of length n over f key. Code word C in code that is C0 up to Cn, so that interpret as a polynomial with the coefficient is the entry of C. In this way, we can see that the code C, is the subset of all the polynomials over F key with degree is less than equal to n. This vector space of polynomial is isomorphic to the question ring F key L over the set of polynomial where generator is fx, where the degree of fx is n. We said fx is polynomial x power n minus 1 because since 1 is a root of this polynomial, so fx is reducible. Indeed, there is a bijection, actually an isomorphic additive map from fkn to the fkx over the set of polynomial generated by fx. Under this map, we can interpret a code C subset of fk to the n as a subset of this question ring. Okay, this is the property. A linear code is cyclic if and only if C is an ideal in fkx over the x power n minus 1. Okay, we will prove that from the left to the right. Suppose C is ideal in this question ring. Let's C is code word in C, and we interpret with be a polynomial with the coefficient is entry of code word C. We have the x multiple with the polynomial cx. We have C0x, C1x power 2 up to Cn x power n. Oh, because this division actually some division in polynomial. So if we have the degree of the the power of is greater than n, so it will change to -1 like this. Gn minus 1 is changed to gn1. Okay. Hence, xgx is in C, sin C is in ideal. Yeah. And cx is in C, because we already know that the code root interpret as polynomial. Thus, Cn minus 1 up to Cn minus 2 is in C. Therefore, C is cyclic. For the converse, if C is cyclic, then for all Cx in C, xCx is in C. But then x power I, Cx in C for all I. Therefore, by linearity, we have the multiplication of polynomial Ax with Cx is in C, where Ax is this polynomial. For all Ax in Fx, thus C is an ideal. So it's more about more algebraic theory in this, algebra theory in this proof. So what we get from this property, there's a relation. C is cyclic code of FKC. Then we have the both side relation, ideal of this question ring. So Gx as the divisor of the polynomial x power n minus 1. Ideal R over I are ideal of R that contain I. Through this correspondence, the polynomial Gx is called the generator polynomial of cyclic code. Suppose GCD of n and k is 1. Let the factorization of xn minus 1 is f1 up to fm. The number of divisor of xn minus 1 is 2 power n. So the exact number, is it actually the exact number of cyclic code of fkn? So for example, find all cyclic code of f2 to 3. So we have the polynomial x power 3 minus 1, and its factorization is this. Sorry. So we have the first the generator polynomial g0 x is 1. So by the divisor of polynomial modulo x power 3 minus 1, we have the set is f2 3. Then the next divisor is g1x is x plus 1. We have this. We have this. And then the cyclic code is this. So actually this is cyclic code too. And then the next generator polynomial J2x is x power of 2 plus x plus 1. We have this cyclic code, and the last is only 0 vector. So how we can get this more easier? Sorry. Let Gx be generator polynomial of cyclic code C of length n. Length n. If degree of Gx is d, then C has dimension n minus d, and Gx up to x power n minus t minus 1, Gx form a basis for C, where Gx is polynomial with coefficient is 0 up to Gd. So the generator matrix of cyclic code we can see in this matrix. So there's a just like move by one entry from this to this, or from the coefficient of the polynomial. Okay. This for Solomon codes and cyclic code. Okay. I think we can continue with the coding theory in cryptography. Uh, just take a minute. Just a second. I want to have a drink. Have a drink.
Bu Julie, there is a
Oh,
question.
there's a question.
Yeah, from Resita. Maybe Mbak Resita will.
Oh, on S code polynomial. Okay, what the relation between A and beta? A. So actually, A is this. So we know that the code is mapped from vector space F key K up to the F key N. So A is vector in this. So how with beta? Beta we choose a distance element and F key.
So we don't have any particular. So we don't have any particular syarat khusus dalam memilih beta gitu ya?
No, we only if only enough with distinct elements.
Okay.
Because
And
we already know because from this generator matrix, because is in F. Oh, sorry, because I think that's trouble with my. Because is a actually beta up to beta n is an F key n. So it's a cyclic in multiplication. So it's have the from the power is have the distinct elements. Okay.
can I ask one more question?
Okay.
Um, from the previous slide, please, how do we know that P and Q, minus Q, have n distinct roots?
Okay. Because this of this. This is the point of why the P minus Q as distinct elements. We choose that beta is distinct. How?
It doesn't seem that trivial to me yet.
Oh. Sorry.
Oh, I think I got it now. So P minus Q has roots
Mhm.
at least beta 1 until beta n. That's why it has n distinct roots.
Yes.
Okay. But the degree is K minus 1. So that's why time minus Q is 0. Is that correct?
Yes, that's right.
Okay, thank you.
Okay, you're welcome. So we will start for the last session of this lecture about coding theory in cryptography using the principle of decoding syndrome. So BQ in 1978, Robert McAleese published a paper that's titled A Public Key Crypto System Based on Algebraic Coding Theory. It is the beginning of code-based cryptography, which built a cryptographic system using error correcting codes based on the difficulty of decoding a general linear code. There's a problem, decoding problem that is given T is in natural number, a general matrix G in F over K, with size is K times N, and a vector R in FKN. We find a vector M in FKN such that R minus M has weight less equal than T. Recall this about the linear code before. Let's see the code over N of length N over FK, distance D. The C can correct at most T. That is the floor of the descent code minus 1 over 2. Let's H be a parity check matrix of key of C for all code word X in FK, for all factor X in FKN. The syndrome of X, they define XX, multiplication of X and X transpose. In FTK, we prove that X in C if and only if the syndrome of X is 0. So we send C, there is noise. The word we have is R, that actually is code word C plus E in FKN. And note from before, SR is SC plus SE. The same with SE. From the syndrome decoding, we already know that the mechanical is compute SR, then find vector E in FKN with weight of at most T, such that the E H transpose is SR. Then we get the forward actually C R minus E. Decoding problem and syndrome decoding problem are equivalent in 1978. Bergkamp, McAllis, and Van Tilburg proved that they are NP complete. Okay, sorry, I can explain you more about this because I don't have time to try to get more. Too many general crypto systems which are based on error correcting code. McAllis first is McAllis crypto system that is to make public key encryption scheme, and the second is nether crypto system. And then actually I'm not yet how many knowledge about cryptography, so I can explain you more about this. But yeah, we will try from the what we have learned before about the decoding syndrome. Okay, first is McAllis framework. K generation, Alice choose NK linear code C over FK by giving a general matrix G, which can efficiently decode C error through the decoding algorithm D. Moreover, Alice hide Z through some scrambling and compute Z prime is equal to SGP, where S is the set of matrix with size is K over FQ over FG, where the determinant of this set is not zero. P is a permutation matrix. The private K is G, D, S, and P. And public K is G prime and T. Auto encryption, let M be factor in FK, both compute MG prime and add factor E in FKM of it at most T such that we get C is equal to MG prime plus E. So C is called ciphertext. Then how Alice can get the message actually? The decryption, Alice compute CP inverse is equal to mg prime p inverse a p inverse. Oh, because of this, we have this G P inverse is MSG plus AP inverse because the weight of AP1 is the weight of E2. So with D, Alice obtain MS. So what actually D? Any of you can answer this? What actually D? Hmm, Anybody can answer my question? Like what actually D in this system? Hmm? Is still anybody in this meeting room?
Yeah.
So what actually D in this system?
D is the decryption algorithm.
Decryption algorithm. How we get
Yeah, the decryption algorithm based on uh Gopak code.
Bapak code?
Yeah, because the proposed binary Gopak code, the backend list.
Yeah, actually this in Gopakot, but it's not only in Gopakot. This even Mac Alice use Gopakot. Actually, his framework is the use for all linear codes.
Yeah, for D in the decryption algorithm, there is the decoding algorithm.
Yes, the
Yeah,
algorithm that we learned before. So we try to get the error by the syndrome.
yeah.
So okay,
Depends on the coding theory that we use for the crypto system.
yeah, that's right. So because Alice obtained MS by using the Symphony compute MS as inverse is equal to M. So the remark is in original crypto system, Alice proposed binary Gopa system just like I said before, but it is in use for all linear codes. And the second, encryption and description are very fast with large public key and size. Sorry, I can explain you more about this. Okay, that's the material of coding theory. Actually, we still have enough time.
Maybe there is any
Um,
question from
yeah,
the
is
others.
there any question? I hope can answer your question. If I can answer the question, maybe I can answer in next time, maybe. We see from the chat. Decryption, okay. Actually, Saada has already answered the question is decryption algorithm. Yes, that's right.
So maybe Miss Ada answer the D that you asked is the decryption algorithm. It's actually the decoding algorithm.
Yes. So we actually have enough much time.
Mhm.
Actually, I want to play a game with you guys. Okay. So actually, this use the what we learned before. Before, is there any volunteer to play with me?
Anyone?
Maybe I'll try.
Oh, you will test. Okay.
Hmm.
Before you test, I prepare my paper. Okay. How we play this game? So you choose one number from 1 up to 15.
1 up to 15.
Okay. Then I
Mhm.
will ask you, is the number you choose is in the first table, second, or up to the seven? By
Mhm.
only say yes if in this table, no
Mhm.
if not. Okay, you get it?
Yes.
But you only can lie once.
Okay.
Okay.
Um,
Okay, you already choose your
yeah, I already choose my number.
okay. From first table, yes or no?
No.
No. Second,
Yes.
yes. The third,
No.
no. The fourth,
Yes.
yes. The fifth,
The fifth. Uh, no.
no.
And the six and the seven is no.
No, no. Okay. The last two is no, no.
Yeah.
Okay. Okay, I will try. Okay. So your number is 7.
Yeah.
Right?
Correct. My number is seven.
Okay. So how with just one you have one life, yes?
Mm-hmm.
So how you can we can get how we can I can get the right actually using the decoding system decoding. So for more this question will be in our exercise. Okay. Okay. I think that's all for linear codes. If
Uh,
still any question, you can have me or my partner Panji.
there is still one question from Miss Ada in
Okay.
the chat.
Oh, particular characteristic of Solomon. Okay. I will try to answer your question. Sorry, I'm not much know about this. We go to okay. So this actually the generator matrix of RS code. So because this matrix is Vandermonde matrix, all the square matrix determine is not equal to 0. So that is the particular of RS code. It means that mm, for column more less than k, the column is linear independent. So and then from this, we are know with some particular condition with the singleton bound, this that the distance is n minus k plus 1. That's my answer. Hopefully you is full your question. Okay, so I think there's not other question anymore, or we will stop the session in this time. How is Saibul?
Okay. Yeah, I think there is no question anymore. We can stop here, and we will meet again at 1 p.m. For the exercise session, right?
Yes.
Okay.
Uh,
So the exercise, have you shared the exercise? So maybe the participants can try it by themselves before the
mhm.
exercise session. Or
So technical, I don't. From Mr. Ua, what's he say?
oh
No?
I think the exercise in the airlock, yeah.
Hmm. Maybe I'm mm, actually maybe just send the material, but
So let me see the airlock first.
okay,
Hmm.
I can stop share.
Oh, exercise. Coding theory. Oh, there is no.
There's not.
No, I can find it.
Okay, maybe I will send only the material. I think so they can read material before the exercise.
Okay, okay.
Okay, just take a minute. I will convert the material.
Yeah, I think you can share the material in from the column chat.
Yeah.